Okay, so the calculations finished. Not sure how long ago they finished, but everything's done. And so if I were to look in my directory, I now have some additional files. So water NIST out.dat. So this contains my manipulated NIST data, along with predictions using Peng-Robinson, SRK, and van der Waals equation of state. Okay, and that's all in this example water directory. Okay, so what I'd like you to do is, if I go back to our team drive in project 1, I'd like you to start by uploading your directory. So I'm going to upload, in my case it's example water. In your case it'd be the name of the system you're looking at. Okay, so it says 48 minutes, but it should only take a minute or less. So good, it's already uploaded, and so now everything is uploaded there. And so what I'd like to do next is I want to create a Google Sheet in which I'll tabulate all of my results. Okay, so in my case I'm going to call this example water, but again you would call it or name it after whatever your system is. And so I'm going to set it up so that on sheet 1 I paste my results from NIST. Sheet 2 will be van der Waals, SRK, and Peng-Robinson. Okay, so I'll name this first sheet NIST. Okay, I'm going to start in column A, row 2. Okay. I'm going to open up NIST out.dat. So in Linux it opens up in something called gedit by default, but you use Notepad or WordPad or whatever it is on your computer. And regardless, you'll highlight all the data. And I'm going to copy it. Then if I go over to Google Sheets, I'm going to paste it. Okay. So remember, this is a comma-separated vector. So all of my data, so all my columns are separated in this case by columns. And so in Google Sheets, if I go to Data, Split Text to Columns, it'll auto-detect this and it'll split up my data. Okay. And so then with the NIST data, okay, these columns will correspond to, first is temperature in Kelvin, followed by pressure. Okay, we'll call PSAT in bars. Then I have compressibility of my vapor, compressibility of my liquid. Look at that, compressibility of my vapor at 280, so 280 Kelvin. Vapor is essentially 1, liquid is essentially 0. Super non-ideal. Okay, molar volume of my vapor, and that's in centimeters cubed per mole. Molar volume of my liquid in centimeters cubed per mole. And enthalpy of vaporization, so called DHVAP, that's in kilojoules per mole. Okay, good. Okay, and there it is in ascending order, going from low temperature to high. Okay. So now I'm going to add another sheet, and we'll call this van der Waals. Okay, I'll start in A2 again. Okay, close my NIST data. I'll open up my van der Waals. I'm going to copy, paste, data, split text to columns. Okay, in terms of headers, okay, I'll go copy my headers from my NIST data. Okay, and all that's going to differ is with my cubic equations of state, I have 2 extra columns. H corresponds to my fugacity coefficient, and I is going to correspond to my fugacity in units of bars. Okay, so this is data not provided by NIST, but we calculate it from our cubic equations of state, and I want you to tabulate it because this we can use to get an idea of over what temperature range is it reasonable to assume that my vapor phase is an ideal gas, where by vapor phase is an ideal gas I mean fugacity coefficient is essentially 1. Okay. Okay. Oh, and again, have it so it's set up so in ascending order, goes from 280 to 640. All right. Vapor is essentially ideal, liquids non-ideal at those conditions. Okay. So add another sheet. We'll call this SRK. Start in column A2. Open up my SRK output data. Copy it. Paste it. And then I'm going to split text to columns. Beautiful. In terms of headers, they are exactly the same as my last van der Waals sheet. Bam. Okay. Then last but not least, we'll add another sheet for Peng-Robinson. I'll start in A2. Close this. Open my Peng-Robinson data. Copy. Paste. Data. Split text to columns. Right? And you can even have it detected automatically. Copy and paste my headers. Okay. And so just like that, you've made predictions for your system using the 3 cubic equations of state. You've also taken the NIST data and put it in a form compatible with the data generated from cubic equations of state. And all of it is in a common working directory, which we now have up here in Drive, that everybody will have access to. And part of the motivation of this is once we make predictions for every system, we want to be able to look at the results as a whole. All right, so within your sheet, that's where you'll perform your analysis. So you can confirm you're all performing the analysis in a consistent fashion, or if somebody needs help, we can help them. Don't copy and paste, but if you are lost, ask me, and in class we can make sure we're all on the same page. But more so, you can look at the numerical values in your classmates' sheets, and these sheets can contain all of the graphs as we use it to try and come up with some overall trends and observations for all the systems. Okay, it'll also serve as for nice record keeping purposes if we take this to be a real project. Okay, and with that, I'll leave it at this. So from within the sheet, you could then add, say, or Google Sheet, you could add another sheet in which you perform all your analyses. So calculating, errors in your predicted pressure, compressibilities, molar volumes, and enthalpy of vaporizations using your cubic equations of state as compared to your NIST reference data. I originally had this built into the MATLAB code along with generating the graphs, but I took it out just to get you to actually play with the data. And then on that additional sheet, you could also put all your plots in it. Okay, and then the only other thing I'll ask you to do besides comparing the NIST data is we have fugacity coefficient and fugacity. We'll use that to try and again get an idea of when we can assume my vapor phase is an ideal gas. Okay, but if you can generate all this data, you are well on your way to completing the project. Okay, and with that, I will end this screencast. Put this on my YouTube channel, make it available to you, so you can hopefully use it and follow along to generate your data.